This is going to be a practice video for thinking through some of the stuff I was explaining to you about for how to think about time, and just because I actually haven't thought through all of these ideas in detail, just for me to figure out how I'm thinking about it as well. So basically, physics in general can be reduced to the concept of the principle of least action, which is essentially the same as saying all of the symmetry groups that make up all of the particle symmetries can be reduced to their identity element in the fewest amount of operation to obtain that other element in the symmetry group. So same thing as saying that photons, because that's the identity element, and it's also more fundamental than space-time per twistor theory, current holography, holographic principle-based theories. So you can just think of all of physics as what this thing called geodesics, which all a geodesic is saying what's the shortest path between 2 points. So for light, essentially. So it'll depend, what space-time you're embedded in. Like if you're on a sphere, then there's 2 ways to go around a circle. So it's, it's going to be depending on which 2 points you're defining for the path. Of course, if you're on a plane, it'll just be a straight line between the 2 points. If you're on a curved plane, it'll start to behave more like a sphere, until you curve it completely, then you can go in 2 different ways. But the thing is that nature, because it's holographic, seems to be embedded into it, this conception of fractional dimensional space, which is, in my opinion, fundamentally a misunderstanding of recursive holography, in terms of the way they're currently framing it as a renormalization. So you go from, a plane to a sphere, and then the sphere can deform, and it normally does, at least idealistically, be this thing called sphere harmonics. So in this case, you can imagine these as going in indentation, so they're lower, and these are normal, or you could imagine them going out and this space in going in. So it has to equal, the amount that it goes in has to equal the amount that it goes out in another area, so that they cancel out just as if it was a regular sphere. So that would be a sphere harmonic. And there can be many sphere harmonics you layer, just like Fourier transforms, to get any other sphere harmonic. You can just keep summing them, essentially, like sine and cosines. In fact, if you were to look at this from the side, the way it goes down and up, and around the circle is the same thing as a cosine. Think of a sine or a cosine curled into itself, into a circle, and then many different angles determine that sphere. Anyways, you pick 2 points, and you say, what's a geodesic? Well, it depends how you define the geodesic, because in this case, are you talking about in terms of space or in terms of the amount of time it'll take to go through that space? So if you think in terms of relativistic terms, in terms of Einstein, the faster you go, the more, the longer you experience time. So you have to think now in terms of VSL terms, like variable speed of light terms, because depending on what path the photon takes, it's going to take more or less time. And so it is faster in one direction or another, and we know that, light that goes through a medium is going to go slightly slower than the actual speed of light. So this is like a real life thing that happens. Light doesn't always go at the speed of light. It's just idealistically through a free medium of empty space. But we know space isn't completely empty. It has this cosmological constant energy density. So based on the last video, I had this idea for thinking about loops in Feynman diagrams. And basically there's this concept of renormalization, which is really important, which fundamentally says that you can think of space-time in a continuum, and you can make a mathematical model of it, but it's going to be wrong, and it's not going to be consistent, and it'll make bad predictions, and when you get into enough loops, which is basically like zooming in, essentially, you'll get infinities and it'll stop working. And that's because essentially this is compressed in time and this is expanded in time. If you keep doing more things in the same amount of time, it's like adding numbers to a number line. You're increasing the continuity, but you can only increase the continuity so much before you get into a kind of continuity that is not actionable in terms of causal influence, like the Planck scale causal influence that we can actually detect. Which is why when you get below that, you get the spinor foam and you have this issue of infinities everywhere in your mathematics. So just logically, this is compressed in time, or you could say each of these actions are compressed in time, and this is expanded in time, because you're saying overall, in terms of this interaction, if you zoom out, it'll have this interaction. So that's actually very similar to an idea in fractal geometry. So fractals, people think, are just self-similar objects. That's not what fractals are. Fractals are a way of understanding how, when you scale the object, so when you make this Sierpinski triangle smaller, how the mass changes of that object. For, regular dimensional objects like a plane or a cube, it makes a lot of sense, and it goes by a power of 2 or 3. And so you say, oh yeah, this is 2-dimensional, this is 3-dimensional. But this goes by a power of 1.585. So the Sierpinski triangle is 1.585 dimensional. That's how the mass scales. Because when you divide it in 2, you actually get a third of the original mass, in terms of not divided into 2. You take the area of it and divide it in 2. So you're making the scale half the size. Then you get a third of the mass. And so you set up this equation. So you set up the scale factor up to some dimensional factor, in this case 1.585, is equal to the mass, which in this case is 3 times that. So you have log base 2 of 3, which will give you 1.585 to figure out what d is. I picked the Sierpinski triangle because there's this 60-degree symmetry, which reminds me of sphere packing, and also Eisenstein primes. So fundamentally, the way I'm thinking about it is this compression of time is like adding actions. It's a lot like adding points in a number line where you're getting more towards continuity. Every single number you add is a composite of primes, right, in a number line. Just like this will be a composite of I don't really want to call them identity elements, but primes are like the atoms that make up the possible combinations you can have. So in a way, they are identity elements. So here's the thing, though. Reduction space, which I also in the longer video had put, but I haven't posted yet. So I'll go back to explaining what a reduction is. Basically, space-time is thought to have these things called a metric tensor, which is a way of knowing what scale you're in, kind of like the fractal. Because the thing about this is that this isn't 1.585 dimensional. If you were to add in all the little triangles infinitely in, not making this bigger, so this is the limit on the outside, but if you added all the Sierpinski triangles inside infinitely in, then it would be in the continuum limit, 1.585 dimensional. So in the same way, space-time in the continuum limit will have a certain amount of dimensions, but it depends how deep you go in terms of the metric tensor. But there are ways that if you're able to put conformal bounds on the space-time, you can say, even if we go infinitely in on the metric tensor, this space will have this amount of dimensions. So entanglement network models, like by Wolfram, look at infinitesimal continuum limit deviations on the metric tensors, and it's like it keeps going, it grows at a certain proportion. So this kind of fractal, if you were to say how quickly is it growing towards this 1.58 dimensional total dimension, if you were to go to the continuum limit of little triangles, that has a certain rate. And so in the same way, you can think of it in terms of these deviations as having a certain rate. And that's important because if all of physics is geodesics, then Penrose did one of the most important proofs ever, which he showed basically that information once inside of a black hole would not be able to escape, and that these have to form, and therefore black holes are real solutions to Einstein's zero relativity, and they have to be real, and eventually they were detected. But it basically just comes from the idea that, you know, in a curved space-time, no matter how you try to escape, the two geodesics will collide. Its current twistor theory is based on the idea that when they collide, they create Riemann spheres, and these Riemann spheres determine a projective plane, a higher dimensional projective plane, which I've interpreted as sub-Planckian per Susskind's model of a holographic principle. So the reason this is a reduction is because now there is a causal connection between these two geodesics, essentially. And this could be split into another point here from another area, but I just did them together. So imagine that one of the geodesics continued. Well then, assuming like a retroactive, so assuming Penrose's retroactive model, as long as it's one reduction away, there is this kind of choice that it can make between reducing to this geodesic reducing to here or to here. But it has to collide, so there's a contradiction. The contradiction is thought to be solved in this way, as in, oh, it'll always just collide. You can't have it then continue, because then there's this other shortest path and it would never have collided there, and that's a paradox. That's not necessarily true. If there's a virtual photon interpretation of this, it can continue and collide here, and then collide here as well, depending on how you reduce it. So the way you think about it is the photons that come in, they just go straight through the black hole. That's like the adiabatic principle interpretation of you just go straight through the black hole, but you also, from the outside, see the person stuck on the surface. So that's like the Riemann sphere when it just collides. But between the event horizon and when the Riemann sphere formed, there's this space where the virtual photon seems to just be continuing through the black hole. But this is infinitely curved, so we can prove that another Riemann sphere will form below this one. So it'll just create another geodesic. And so you have these layers of geodesic reductions that is the entanglement network. It just continues, and this is creating the projective space inside. So the idea of the Lincoln tunneling is this idea that you can create a vacuum out of increasingly tunneling singularities. The kind of singularities you tunnel will determine what kind of vacuum you have. Really, it's the structure of the singularities. So imagine you're on the surface of the black hole, and you have a bunch of photons hitting this area and this area. Well, then there's this thing called cohomology, I just wrote there, that says that you can't make a global reduction and a local reduction, because by the time you make one local reduction, a different local reduction will say a different answer. So you can't like save the states, go over here to check these and then come back, and by the time, this is like a light cone, by the time if light were to go this way to check and that way to check, they wouldn't be congruent. So there's this also other concept of like a Fibonacci based spiral for the most compactified way to put points on a sphere. And if you wanted to, renormalize, you're renormalizing to a reference frame. Like you can't renormalize in this case to like the most compact method for sphere packing across the whole black hole, because photons are hitting the black hole in many points here or here. So each of these are acting in their own way, like a singularity on the surface of the black hole in terms of complexity. So kernel divergence are these ideas where electromagnetic fields, they have this flux essentially, and divergence means you just go away from the point, curl towards the point, and you play with these and you get all these electric field lines for the electromagnetic spectrum. The best way to think about all of this and why it's so confusing is actually in terms of pure mathematics. And it has to do with our misunderstanding of time, and then later I'll go back to physics for it to explain antimatter and this renormalization problem. So now think of each of these as one of the circles on the surface of the black hole. Like, if you start the pattern growing from one corner or another, that's like a different perspective on the dimensionality of that area relative to another area as you're reducing it. So I just thought of the idea that numbers are orderable. Like if you look at surreal number theory with Conway, he basically says that numbers, like he proves, you kind of have to read it to understand it's pretty abstract, but you basically have a method for looking left and right of a number infinitely, and you can produce every single number in the one-dimensional real number line and extend that. So that's the limit before you get to imaginary numbers. And these surreal numbers can't be ordered. They actually represent game structures. And the way I think of cohomology is that it's fundamentally this. You can't order the reductions because any possible order is just as viable as any other. Although, once you're in your local reduction space, you can order those numbers. Those numbers are like identity elements, like possible. I measured that this is the one that happened to this one before it made this interaction. Like this is the version that happened. I made that reduction, I measured it. So that's an ordering. But you can't start ordering here, start ordering here, and start ordering here, and then meet up and have a global ordering of everything. It's always going to be in reference to a local reduction. So that has to do with reversing time, and that's really important. But okay, now I'm going to go back to the math-based interpretation. So if you can build everything out of primes, all of the numbers, you divide primes, you get the rational numbers. You do it in terms of improper fractions, and you get irrational numbers, and you can do it in terms of non-algebraic, transcendental numbers, and you can continue all the way to surreal numbers. What is that? Really what you're saying is a combination of primes. Like 7 is a combination of the primes 2, 5, 2 2s, and 1 3. Or you could say 1 5 and a 2. So you can make 7 in different ways. You can reduce it, you can have different loop diagrams that determine that state. So how does that become actually useful for physics? Well, there's not just one-dimensional primes, there's also n-dimensional primes. So the way to think about it is in terms of limits, right? If you're taking the limit of some function as it approaches a number, you're going to be defining it in terms of a set of reductions. And a lot of times these get reduced to Fourier series, which is why I just wrote that there. And you can take a left or right-handed limit in one-dimensional mathematics. And so it looks like you're going to be reducing in one way or another. And that's a lot like how we think about time, past or future. But in the complex plane, you can take a limit towards the origin, for example, like you can take a limit here, or from here to here, and technically there's multiple limits because it's not continuous, but anyways, here to here is another limit. So this looks like maybe in reference to a reduction in one-dimensional space, like you're reducing to the past. So it's just here to here. This is the same as this in reduction to one dimension, but it's not at all, right? It's embedded in this two-dimensional space. This looks like it's just to the future. This looks like it's just to the past, but it curled around and went back to the future and then to the past. And so that would be like, producing like antimatter producing a regular particle, and then it would be, it's just an analogy for how reductions in terms of producing some state. So that seems confusing because Okay, think of it in terms of 2 dimensions. Now you have multiple 2 dimensions. These are like holomorphic functions. They look kind of like this, like intersecting surfaces. This is matter. This is antimatter, for example. There's this problem where if these collapsed, right, if they were just one plane, you just squish them together, you would say, these are the same. Like, this is just a one-dimensional line, and this is just like antimatter is reversed in time all the time. But that's a very poor way of thinking about it. A better way to think about it is, I'm not sure if I actually drew this on the wall. Okay, yeah, over here. There's this light cone interpretation. So, I mean, I'm just like saying this is sub-Planck, so it's like not causally associated to the light cone. A light cone just means these are the possible geodesics that could have happened, basically. It's like the possible alternate Feynman loop diagrams. And so you get this average when you take the actual reduction, when you measured it, you chose which numbers we were going to use in your Fourier series and took the limit, and you get some antimatter reversed in time, but it could have been in any other angle. It was just an average. It could have been this way or whatever. This is not the reality of these geodesics. In real life, geodesics in whatever dimensions is going to have curves, right? So you're taking limits in terms of these complicated curves in whatever n dimensions. I just went up to 2 dimensions to make it simple. And so when you take the average, it'll always look reversed in time, but if you looked at each individual detail, you'd know, oh, what it takes to make this extra loop in the Feynman diagram loop is this like strange conical, like sinusoidal function in terms of how this geodesic works, or set of geodesics works for this particle. But if you reduce this to 1 dimension, just like how I said, here to here is the same as here to here if you reduce it to 1 dimension. If you reduce this to 1 dimension, it just looks like you're going forward in time. No matter how you go, you're just going forward in time, and the antimatter will always just be reversed in time. And so that's important because, okay, so you say, well, I can construct all the points in 1D out of primes, but what about 2D? Well, in 2 dimensions, there's this idea of Gaussian primes and Eisenstein primes. So these are like more like Eisenstein primes because they're connected by triangles, but just to give you a general idea, the way when you zoom out in a conformal field, they can be defined in that conformal field. You can determine the complex numbers that you can build all other complex numbers out of, essentially. But here's the issue. It would be like putting another line in the middle of your line. Like if I put a line here, between here or here, from negative infinity to infinity, in between my other line, it would kind of mess up the ordering of my numbers, right? And I could just keep doing that. Same way, if I make another origin on the plane, another singularity for reductions, they're going to mess up like a wave interference in terms of the primes. So why is that important? Well, it has to do with this idea of fractional VSL time or space-time or whatever, which is this idea that in every Planck length, so the black hole surface, again, holographic principle-based Susskind Planck length from which we're projecting the internal space of a black hole, each of these has also another Planck length, and those Planck lengths have its own Planck length, because it's just like saying if you go past what's causality, you're going to get more geodesics. Like you're just going to get more of that stuff. It's just from the perspective of one, you have this limit, which like really these cones, this next cone should be smaller than this point. And this one should be smaller than this one's point. Like it's really, this would get really small. This is just as an analogy. It's like the Sierpinski triangle, right? Like you get these super tiny triangles that really are having almost no effect in terms of your dimension. But if you were to zoom in there, it would have it look like it has its own structure. Of course, this is a perfectly crystalline fractal, but you can get fractals that are rough. Well, I'm just basically trying to explain how you can possibly get a real rough fractal. And so here it goes, basically. So you have some particles, and they're inside of a black hole, and there's a projective space for how those particles are working, and they're going in some direction of time, and you reverse all of that. So you're reversing perfectly all of the reduced Feynman diagram loops that happened. But that's not the real state of those particles. The real state of those particles is the way they were projected from every possible circle you could have written on the surface of the projective space. Right? You're only experiencing a reduction of that average, of this possible average. So you chose at arbitrary a way to start reducing. So you chose, one point to start reducing from, and then you spread your light cone whatever way. That's the same thing as going to the surface to one of these areas and starting to reverse these surface reductions in terms of the entanglement network of the geodesics coming into the surface of the black hole. The reality is just the surface of the black hole, essentially, but it's the whole surface. But we're only seeing part of the projection of part of that surface. And so you start reversing these, right? But that's connected to geodesics between the outer layer of that universe's, the black hole around that universe, which also has this surface. And so you're reducing from that point, you're connecting to some other point on the surface of that other layer of the black hole. But these deviations, in terms of holography, just by logic, would be smaller, right? Because the change, once you start reversing all of the particles in the universe, eventually, you'll start from this point and start reversing everything on the surface of the black hole from that point, from here around, right? But the stuff happening on the surface there is still part of the projection of part of the surface on another black hole. But the amount of change that you're doing is very, very small while you're reversing all the information in our universe relative to this one. Because once you reverse all of the information, eventually you'll just get it into the surface, the interior surface of the black hole, and it'll just go back out. It'll shoot back out of the black hole and follow the geodesic path that it did over here to here, and then do the same thing. So the amount of time that the light spent on the black hole, the amount of, relatively, because it's subplanckian to that universe, was like nothing. You have to get out of the black hole to start saying, now I see the changes that you made. Because the subplanck effect can just keep happening over and over and over. And to this in-between universe, it's like you haven't changed anything yet. So that's like recursive holography. And that explains the issues with renormalization. Because if the complex, whatever interactions are happening in the continuum of our space-time are influenced by this infinite series of layers, but they become so ridiculously small, these are the higher order error corrections that you need to understand what's going on in those particle spaces, then, you can just say, I don't need these, that's at the Planck scale. It's like, that's beyond the causal order of what I care about for reductions. But you need that information. In fact, you need it all over that surface of the black hole as well, if you really wanted to model what's actually producing your local reductions. And that was probably still too abstract, but basically this is like saying one-dimensional primes are building up these states or series in the elements in a Fourier series. But that's one of the possible way that could have been projecting it. So you have many interpretations of the one-dimensional, right? Like, you can have this in any angle you want and rotate the plane and put a line through it, it'll still be one-dimensional. It still seems like it's one-dimensional to you. Then there's the two-dimensional interpretation, which is this spinor foam, really. Because this structure is fractional dimensional. It acts like we're one-dimensional in whatever, 1.58, etc., whatever the surface looks like if you look at it from the top. And so that's when it gets pretty abstract, because you have these, obviously these reduction spaces that overlap other reduction spaces. So combinatorially, you get a ridiculous amount of, so then how do you know which ones are important? to capture the most amount of information. And I mean, I haven't thought about that completely yet, but basically there's this idea, very simple idea, for understanding when you scale into a fractal, like how many of these squares touch it in a grid. You increase the grid more and more, and it gives you a proportion in terms of the amount of squares it's touching that helps you calculate the ratio for how the mass is changing, which is how you get that equation to take the scale factor to that dimension, which equals that change in mass. So you know the change in mass by how it's scaling, and then you set that equal to whatever you scaled it by to some power. We just say d for dimension, and then you solve it with the logarithm. But what if your grid isn't just two-dimensional? So it's not just 2 to the power d in terms of how it's scaling. But what if it's fractional dimensional? Like what if you embed it in a Sierpinski triangle? Well, that's what I'm basically saying that the surface of the black hole is when you choose to start reducing it in a certain way. When you choose a rule to how to start reducing it, you're treating it with that fractional dimension. Of course, the whole surface, you'll never be able to measure the whole surface at once. But if you started measuring from every point, there is a basis from which you could say this area is now 1.3, and this is 1.7, this is 1.8, and this is 1.2 on the surface of the black hole. And those are called fractal basins. There's actually a map that shows basically that's how it works. And you can continue this grid idea into higher dimensions. But, and this is just the idea of Vilenkin tunneling us, just thinking like, in terms of holography, like, you may be in one layer of this fractal VSL continuum, and you may be getting influenced from Vilenkin tunneling from another layer above it, essentially. And so you can think of it as a plane or a structure, because it's not really a plane. It really would be more like a membrane looking like some weird fractal dimensional membrane, which is really entanglement networks. That's what they're basically doing. Wolfram's basically doing that right now. Trying to model them. They're too abstract to really model well, but and it's passing through, picking up and entangling to that Vilenkin tunneled structure. Whether it entangles or not is basically the same as saying whether it reduces or not, or just acts space-like, not time-like, and you know there's no geodesic between it essentially. So if there's a geodesic, it's time-like. If there's no geodesic, it's space-like fundamentally. And it's kind of hard to explain. Now, yeah, I'll just go back up here. So every black hole, just light hitting it, just seems to just go straight through. Of course, when a black hole's really truly active, there's a ridiculous amount of thermal energy on the surface. So anything that goes to hit it will turn into just pure light, and it'll go through as pure light. But even an empty black hole, the information that goes through will just go through as pure light. It's essentially a white hole, right on the inside, if you think about it that way. White holes just spit out energy, black holes suck in real information. But the information that gets stored on the surface is projecting that white hole radiation. And so I'm just saying that as you continue, it'll still have that structure. Then the issue becomes the inverse, of course. We know that black holes have Hawking radiation. Hawking radiation is the same thing as these Riemann spheres being entangled to each other. It's the same thing as the entanglement network nodes being entangled to each other. ER equals EPR, where they say essentially that a wormhole is the same thing as entangled particles. Hawking radiation is how black holes entangle to each other. And there's something about, if you have like a surface of one black hole entangled to another surface, or it's entangled to itself. Like, there's a period in which black holes can be close enough in an early universe to be entangled to each other. And then eventually, through dark energy, in a hyperbolic space, they'll just get ripped apart and there's no way. They'll stay entangled, partially, on different parts of their surface. But they become so far that, I mean, being entangled is an instantaneous thing. So what is it? Why is it instantaneous? Well, it really has to do with the projective space on the surface. So these spaces, in this space, you can have a model for a universe in a hyperbolic projective space that you're reducing from, and say this black hole's entangled to this one. And what does that really mean? Well, there's two black holes inside that are, you know, trillions of light years away now in a dead universe that has expanded from dark energy, but they remain like really close to each other on the surface, entangled to each other. So this has no bearing on the entanglement network structure as you consider the layers increasing. It's like, this is like the surface of a hyperbolic conformal space, like where you go towards the edge and it just gets smaller and it looks the same. It would be like, actually I don't have a good drawing of it here, but fundamentally we only think in terms of one-dimensional time, but you can think in terms of one-dimensional time embedded in 1.5-dimensional time, or you can think of two-dimensional time embedded in three-dimensional time, etc., etc. And you can reduce, you know, like I was saying, you can reduce it to saying this is just in the past. But it's relative to a reference frame of reduction. That's basically the idea. And antimatter is, the way we can measure it, always going to be an average of that reduction. It is not representative of the real possible states that matter could be in. And also, the fact that there's alternate reductions doesn't mean that every single possible thing that could happen will happen. Those are determined by the possible alternate geodesics. So there's always going to be a light cone in terms of the possible geodesics. And we misinterpret it because we only think in terms of one-dimensional time.